Thank you very much, Rima, for this kind introduction. And I will briefly add two things which are also in my heart right now. It's the ERICA project, where I'm happy to work for the European reference networks in the European Rare Disease Research and Coordination Support Action Program, which is funded since, I think, March this year. Also, I'm very happy to be part or to be co-coordinator of the Randomization Working Group, an international collaborative working group from industry, academia, and so on, working together on the topic of randomization. And I'm also would like to mention that I'm in the scientific review board of the ECRAN. Anyway, I will stop saying something where I'm involved in. So I will come to my matter. Does randomization matter in rare disease clinical trials? And I will go to my first slide. So my main objective for today is that I would like to show you ideas to identify the best practice randomization procedure you can use in your rare disease clinical trials, and use this approach rigorously also in the analysis. So I'm start with background, and then the other 6 topics are, what is randomization and what it is not? And then we come to the third part, what randomization can help us to do in particular rare disease clinical trials. I will give you some ideas about that. And then we end up our preliminary consideration and start working on what are elements of a structured choice approach for finding the best practice randomization procedure. And then I tell you something, which approaches did we develop right now? And I made some final remarks. So that's our way for today. And our background. Well, what are the background and learning objectives? So I hope that everybody of you has some background knowledge on the process of treatment allocation and how it works in clinical trials. And also that all of you know what random allocation is. I will not repeat that in a very detailed way. So what you will learn and understand after the webinar, I hope, is that you take the value of the different randomization procedure back to home, that you know that no randomization procedures fits to all purposes you can have in your clinical trials, that you understand how to select a randomization procedure based on scientific arguments, and you know that there is a special importance on randomization in randomized clinical trials. The discussion is very strongly connected to what we call bias, because randomization is mostly done to avoid or mitigate bias. And so I will dealing also with the subject of bias at some places, but I will not deal with other methods and to reduce bias than randomization. I know there are other methods available, but I will not deal with that. Okay, so what is the mode of action of randomization? Let's discuss this. Okay, what we have is that randomization has a long history, also in, let's say, in trials connected to health or to medicine. And one of the oldest example is the example of the physician, the Flemish physicians. As I'm a half Belgian people, I like that very much. So the Flemish physician, Jean-Baptiste van der Mont. And he suggested in the 17th century let us take out of the hospitals 200 or 500 poor people that have fever, flourish, and let us divide them into halves. Let us cast lots that one half of them will fall into my share and the other in yours. I will cure them without bloodletting and sensible evacuation, but you do as you know. So basically, the procedure he suggested as the randomization procedure, I would say, is a random allocation rule, which is a very famous, very old procedure, because this procedure makes the preserves the allocation ratio by 1 to 1. Later on, there was a well-known example from the MIC in 1948, which is the well-known streptomycin trial, a randomized trial to cure tuberculosis. And this was here the randomization was coming into place by Bradford Hill, and this was, let's say, some sort of game changer in that direction, because up to that point, a very well established, let's say, allocation procedure, they call it in this time a randomization procedure, was the alternating sequence, which is nowadays not considered as a randomization procedure. So what does the regulator say in that perspective? Well, randomization introduces this ICH E9 guideline. I've copied this part from. Randomization introduces a deliberate element of chance into the assignment of treatments to subjects in clinical trials. During subsequent analysis of the trial, it provides a sound statistical basis, first aim, for the quantitative evaluation of the evidence relating to the treatment effect. It also tends to produce treatment groups, second aim, in which the distribution of prognostic factors, known or unknown, and the latter is the most important part, unknown risk factors or prognostic factors, are similar. And the third aim, in combination with blinding, randomization helps to avoid possible bias in the selection and allocation of subjects arising from the predictability of treatment assignments, what we call nowadays allocation bias or selection bias. So these three aims, randomization should provide us or should help us to do. And most of the people think more in some way in other directions. But anyway, we will discuss this in a couple of minutes. So this is also expressed in the ICH E8 guideline, where we have a different statement to minimizing possible bias. What is randomization not? What can it not done? Well, there's a recent article of Collins in 2020 in the New England Journal of Medicine, and well, he wrote a paper about the magic of randomization, where there's the myth of real-world evidence. And in this article, it is stated that the assumption of randomized trial is not that the patient population studied is representative for all patients you can have. So you will not get a representative sample by the randomization procedure or random allocation process you apply. Then you have to do different or other things. That's very important to say. On the other hand, by the way, Collins concluded that this special importance of the randomization process or the random allocation process can mitigate bias on the one hand, and that is not possible in observational trials, as, for example, you have in real-world evidence. You must take that into account. So this is rather a very high standard. Random allocation is not random sampling, not a representative sample is coming out, but it avoids bias in the best way you can do. So how will we implement random allocation? So let's go one slide. Well, the easiest way you can do that is by tossing a coin. So check, and you have treatment A, check, and you have treatment B, and so on. Nobody would do it like that because it's not reproducible. We have no computer programs for doing that. But what we are doing is when we implement this tossing coin process is our best standard. I would like to say this in this way, it's complete randomization. You can have all allocation sequences you can think about as a result of the randomization process. Unfortunately, also you can have that only people are allocated to one of the treatment. That's also possible by tossing a coin. So that's not very much likely. But the chance of having that is very small if the trial is getting larger. So more patients are in the trial. And so complete randomization has its value in randomized in the implementation of a randomized clinical trials whenever the study is large, but we do not have this when in rare disease clinical trials. There's another group. So the Van Helmont procedure is the random allocation rule, which is splitting the total number of patients in two halves if you have two treatments, one getting treatment A, one getting treatment B. And if you do that in smaller parts, this choice, we call this blocks. So let's say you have a trial with 100 patients and you put a block of size 10 and you say, okay, I put the random allocation in these 10 patients. Then we are talking about what is meant by permuted block randomization. So of course you get 10 blocks of size 10, and after each of the blocks you have balance. So the same number of treatment allocations to A and B. Of course, a block size 10 makes 5 to A and 5 to B. So this is the rule where a strict final balance, so at the end of the randomization, we have final balance, is implemented. There are other possibilities where this property is relaxed. One way was based on what I told you about complete randomization with tossing the coins. You can have this unfavorable allocation process that all people are going to A, and so you cut this unfavorable allocation sequences, and that makes big stick design. And if you make that uniformly probable, you get the maximal procedure from Vansberger. On the other hand, there is an idea of Efron in earlier days who says, okay, we do not have to cut. We just have to not to choose a coin which is fair if the number of allocations to A and B getting more extreme in one way. And so he makes that in probability. That's Efron's biased coin. And a combination of big stick and Efron's biased coin is proposed by Chen. And so on. We have so many procedures. So more, I think every people knows block randomization. It's the mostly used procedure, but the others are better. I will show you. So what randomization can help us to do is my next question. I start with my very personal impression. So what theory tells us is that no randomization procedure performs best with all criteria. I show you some examples of that. So that's also stated in the book of Bill Rosenberger in 2016 and articles of Anthony Atkinson who elaborated that very intensively. But what is the communication with scientists? Well, what applied scientists mostly feel about randomization is, well, that's nice. We need that because we would like to publish the paper, but well, it's more a must because my patients are so heterogeneous, or I need to block this. I need block randomization. The principle is not really clear. What can it do and what it cannot do? And then they think, okay, if I end up with an unequal allocation, so I have more patients in treatment A than in treatment B, and I intended to have one-to-one allocation ratio, that's worse because of the power. Oh no, that's not correct. And then they would like to balance covariates. That is mostly important, so they stratify. And that selection of the procedure is more a problem of availability of software than of other things. And I try to show you that it's not true. And okay, what the literature mirrors us is there is less or no training on randomization. I do it now, and I do it frequently in my classes I hope you enjoy. And there is also no recommendation to give a scientific argument for the choice of the randomization procedure, a scientific argument. You can do something, there are recommendations, but to elaborate that scientifically. Okay, what did we do in the randomization working group? Oh, I'm so happy that Alex is also here. He is the driver of the paper I have in hand, what we published this year. And it is stated in that paper that randomization should help us to mitigate selection bias due to an investigator's potential of selectively enroll patients into a study. Here's a freely available BMC paper. Randomization should help us to tendency to promote similarity of treatment groups with respect to known and unknown confounders. That's also stated in the ICH guideline, very brilliant, and an important role of statistical analysis. And what is also stated in the paper is that we have to take into account from time to time or from situation to situation different kind of biases. For example, the most important part is what we call the selection bias or allocation bias. And a procedure who mitigate that should have a high degree of randomness. And other procedures are should minimize chronological bias. Chronological bias is if you have a time trend in your data and early patients have a worse prognosis and later patients have a better prognosis. We see this in surgery trials, for example, where surgeons have a learning curve. So random allocation can mitigate selection bias. So that's the main story. So let me give you very small example about very small comments about bias. We have allocation bias or selection bias and chronological bias. Allocation bias is if the investigator know or predict which intervention the next eligible participant is supposed to receive, and that is a synonym for selection bias. That may influence the way the investigator approach potential eligible participants and how they are assigned to the different treatment groups, thereby selecting participants with good prognosis into one group and more than in the other group. So it's sometimes unconscious and not a very conscious process. So chronological bias is, as I said just before, the study participants allocated earlier to an intervention are subject to different responses from participants who recruited earlier. Well, And I here refer to other definitions of biases in the catalog of bias, which is on the website of the Center of Evidence-Based Medicine. So now we're going more into detail. Let's go ahead. So I have a paper, and this paper is from McDonald in the Lancet 2017 for Duchenne muscular dystrophy patients, a multicenter randomized double-blind placebo-controlled trial for all-terrain against placebo. So what did they do? They applied in, as you can read in the paper, a stratified permuted block randomization with block size 4. Great. They have 220 patients in the trial. And if you have block size 4, then you have 55 blocks. Great. But on the other hand, they have done this stratification, and they involved 3 stratification factors with 2 levels, making 8 combinations. And if you intend to have this, to follow this idea, to have a balance in the stratification levels, then you see, okay, 55 is not divisible by 8, so that makes a problem here. Okay, I would not make it too complicated. So let's make, for the next discussion, simplify the approach a little bit. Let's go ahead with the with the permuted block of block size 4, and let's ignore the stratification at that point, and let's go for some other reasons to a sample size of 240 patients, because it makes it a little bit easier. You will see in a couple of minutes. So what means block size 4? In every block, you have one of the 6 potential blocks available, which are depicted here. AA, PP, AP, AP, and so on. And I marked in red, which is a so-called deterministic allocation. Why deterministic? Well, if you know the past of the patients are already allocated, and you know where you are in a block, and you see that after 2 A patients, there must be 2 P patients. So 2 deterministic allocations. Well, there could be 1 or 2 deterministic allocations. Okay, if you know what is going on in the trial, and if you have an idea what is allocated up to a particular point, you know from the permuted block randomization of block size 4, you have 60 blocks of size 4 to reach the 240 patients, making 60 to 120 allocations, which are deterministic. Well, any deterministic allocation you know in advance, you could select a more favorable patient, and that introduces bias. That's a remarkable amount of patients which may show a deterministic allocation. So Blount and Altman suggested to vary or to use other block sizes, and interestingly, they advocated for block size 2, 4, and 6. Well, I go the other way around. I increase the block size. And what you see is, if the block size increases, you have a potential for 3, 2, and 1 deterministic allocations in the 15 potential block sizes of block length 4. So that makes 40 to 120 deterministic allocations. The 120 is kept, but the 40 is going down. So that means by increasing the block size, the number of potential minimal allocations decreases. So that advocates smaller, larger block sizes, and it clearly shows you from this point of view that random allocation rule is the best procedure you can have when you are doing permuted block randomization. And here is the rule for constructing the deterministic allocations. Well, on the other hand, well, what I discussed right now is only the fact that we have deterministic allocation, and it is one metric, and it is not really related to my concrete trial, to my concrete disease, to my specific setting. So we can do better. So, but what is about the argument that the planned number of allocations at the end, the allocation ratio should be preserved? So I don't think that is really an important argument, because if you think that if you, for example, have an unbalanced allocation at the end, and you have a loss of 3% in the power, then you can deviate very much from the balancing, from the one-to-one allocation procedure. So it's I give you an example later on. So I think that even if you, let's say, intend to have a one-to-one allocation ratio, it's not a mandate. It's not very important to preserve that at the end, because the loss in power is very small for a very broad range of unbalanced frequencies at the end. And you will do that with missing data every time, and overrunning and underrunning every time. No problem. So, and what is about balance heterogeneity in patients for stratification? I come to that in a moment. I will have so much discussion with that, so I will avoid that discussion right now. So what we want to have is what is given in the James Lind library, said that we would like to have a treatment comparison which is fair. And that is most important thing. And that is done by, if we avoid predictability, because we know that a predictability forces allocation bias. And if we have allocation bias in our thing, we have less credibility in our study, the validity of our trial results is less, and so the reproducibility of our research is also less. And I would like to show you an example which I showed at a meeting where we presented the results of the Asterix, Inspire, and Ideal project at the EMA, which is a very old example, and show you what happens with allocation bias in trials of different sizes. I use again block randomization with block size 4. My allocation bias, I go into detail in a couple of minutes, but I will show that as an eye catcher right now. So my allocation bias effect, which I allow for every patient, is 25% of the effect size you would like to detect in your clinical trial, right? So you can say small, right? Okay, so we have a trial of a total sample size of 8, 20, 40, 80, 200, right? And I put the permuted block randomization, and from this I constructed the type 1 error probability of a clinical trial under the null hypothesis. So there should be always kept the 5% level, but I have this unfavorable problem of the allocation bias, in fact. And you see that only with the small trial, the 8, you have the chance to go below the 5% level. All other seems to have a tendency which is increasing. So you might think, okay, that's fantastic. I make a small trial because then I can rule out the allocation bias. Well, that's not the statement of the story, because the range you have for the p-values, for the actual type 1 error probabilities is rather large. And that's not a good part of the story. So there is a particular problem for smaller trials, and you cannot be sure that there is really a treatment effect or not in that point. So what are structured elements of an approach? So we worked on that in the IDEAL project, and I was influenced by an idea which I got from Norbert Bender from the bee farm in Germany, who make its habilitation, where I was a reviewer of. And he said that if you do a trial simulation, you should have a structured approach. And I said, well, that is my story. And I transferred that idea and put the so-called ERDO statement. ERDO is for me the evaluation of randomization procedure of the trial design optimization. Well, I can do that before the trial starts, and I can recommend something which is the best procedure. That's the good news. And I only need the design specification. And then I do my simulation study in before. So, well, not every biostatistician likes that. When I submitted the ERDO paper, I get a comment from a reviewer, and he said, I have so many things to do with planning a randomized clinical trial. I will not accept to do anything more like this. Well, I think he lost a chance to improve his clinical trials. And I think what you have to do and what you can do is a good thing, because you have more valid observation. So ERDO is a structured approach, and we have the software available, and we have methods available, and we can do that for almost all scenarios which are important. So it's more a benchmark process for the choice of the randomization procedure. We start with to quantify the effect of allocation bias on trial results. We also can include chronological bias, but that's not my topic today. So I will lose that way a little bit. So, and what I focused mostly on is on the type 1 error probability. And I would like to keep the type 1 error probability as low as possible to make valid statements. And I will recommend the clinical situation. So what is I will consider the clinical situation. So what is the clinical situation, which is based on the effect size you would like to detect? It's the design of the clinical trial, right? It's the number of observations, and so on. So that's more my clinical setting. Primary endpoint, is it continuous or not? The minimal effect you would like to detect, which has a strong relation to the sample size. The number of treatment arms. The design, is it crossover, or is it parallel group? Do I have stratification to identify? Is it adaptive? So do I have interim analysis? That all is coming into my design, and I use this information in my trial simulation. So these parts, sorry for this transparency. It's much more formal. But what I would like to tell you is that we have a formulation of the allocation process, which is based on the difference in the treatment allocation to treatment E or C, when I patients are included. So the actual imbalance after I patient. And we have that for different trial situations. And we have a model for chronological bias. And that's the unique part. We can model this. We have a possibility to describe this bias, and by this we can quantify, not qualify. Well, this trial has Hawthorne bias or something like that. Nobody knows what it is and how it affects my data. Every is subjective. Here we can quantify this by having a model for this. And that makes it interesting for the researcher in the planning phase as well as at the end. So model bias specification. So now we have, because we have this bias model, and it is acting on each random allocation sequence. Now we have to combine these overall allocation sequences. And that can be done by various measures. So one people think about power, one people think about imbalance, other people think about correct guesses, other about deterministic allocation. My favorite is, because the ICH A9 guideline says that I have to quantify the contribution of bias on the p-value. So type 1 error probability. So how can I do this? Well, I'm sorry for the next transparency, it's much more formal. Well, having an allocation sequence, I can calculate the type 1 error probability for that allocation sequence. That's fine. So for every allocation sequence from a randomization process, I can calculate the type 1 error probability when allocation sequence plays the devil in my trial. Okay. And the summary is often done by summing up, taking the mean value. I don't like that. I have a preference for the go, no-go criteria, saying how many of these type 1 error probabilities I calculated are below the 5% level. I like that very much because, I hope the regulator will support me in that direction. I think they would like to preserve the 5% level at the end. Okay, good. Actual type 1 error. So we're going back to an example. Enough formulas for today. So what can we do? Okay, we have this 240 patients. Okay, we have the 240 patients, and we will compare the effect of allocation bias. Let's say the effect of allocation bias for various. No, sorry, I lost it. Sorry for that. We will study the different allocation bias effects on the type 1 error. Again, I put a box plot here, and you see if the allocation bias is rather small, so 5% of the effect size you would like to detect. So that means you have only twins in the trial, right? You cannot distinguish them, yeah? Okay, then, you have a slight deterioration of the 5% level. It's not so much, but then you see that that increases dramatically if you have 10, 15, and 20% of the allocation bias. Well, we can discuss how many allocation bias would be reasonable. I'm working with 5% because on a conference, some of my colleagues was very friendly and I said, that is too much allocation bias, too much effect. So I will be very conservative, 5%. 5% of the treatment effect is suggest to allocation bias. What is the effect on my trial? So you see that the actual type 1 error probability increases with the magnitude of the allocation bias effect, eta. And now the question arises, can we do better? Well, I already introduced some other procedures, and we can go to other procedures. So, wow, that's amazing, isn't it? Well, we have complete randomization. We have random allocation rule. We have permuted block randomization. We already know that. The deterministic allocations are high, but also in my criterion, it's not a favorable procedure. We have permuted block randomization with larger blocks. It's going down. We know that already. We have the big stick design with imbalance margin 14. I allow a large imbalance at the end of 14 patients, where you might say, okay, I can allow more. Yeah, we can evaluate that. And we have efforts biased corn. And you see here that why I don't like the mean of the p-value, because rounded up by 2 digits, it's always 0.05. It's only a rounding problem. Well, you see, well, there's not so much deviation from the 5 levels, but I have only 5% allocation bias effect. But you see, in my go, no-go criteria, you would prefer complete randomization. Well, you might not like that because of having a potential for a trial where only one treatment is allocation. So then you should go to, let's say, to big stick design, because it's 39%, and the go-no criteria for complete randomization was 44%. It's comparable. But even random allocation rule is not worse as the others, because they are 0%, preserving the type 1 error of 5%. So go-no criterion seems to be sensitive. Large difference between the procedure is observable, and you can do that simulation by picking up the allocation bias you think which fits best to your design, and with all the other perspectives like sample size and so on and so on. Okay, what can we do at the end of the trial? Because I have a model, I can quantify, I can put that in the final analysis. I can put that as a cofactor in the analysis. That's great. I can use my model at the end of the analysis to quantify the effect and to see what happens. Well, I did a simulation, I'm only a slide simulation to visualize that you have an impression what is going on with this kind of let's say analysis. Well, if you put the unadjusted analysis, you see the analysis, you would go with the data which you have in the trial here. That was given in the paper. And with my simulated data, I got a p-value of 0.716. Well, that's not the data in the paper. It's my simulated paper. So don't mix that with the data. But what you see, the interesting problem that is not significant, right? But now I did a reanalysis, a sensitivity analysis, and I included my bias model because I already know that under the simulation I included this bias in it, and I included it. It does not have a significant p-value, but it extracts variability from my data. And now the net treatment effect is significant. So you can have situation where this bias overlaps the treatment effects, and so covers the treatment effects, or you can have the other way around as well. So here I put similar a treatment difference like in the above scenario. I have an unadjusted p-value of 0.0487, significant, but if I do the reanalysis with the bias effect, I found that the treatment effect was let's say, promoted by the bias. So you can have both situations. Okay. So the next question is, can that be done only for a clinical trial with a parallel group design, with a continuous endpoint, with, let's say, no interim analysis and so on? Well, let's go to the developments right now. Okay, what we did since we got the grant for the IDEAL project, we did a lot. We published the ERDO paper, which was the basis, and then we published other models for other situations. For example, we considered that for a multi-center, two-arm continuous and primary endpoint variable situation, and that was also that was published in a paper in 2019. Then we had a two-arm unbalanced situation with time to event primary endpoint, and that was done by Marcia in 2017 and 19. She did that. Then we have time to event endpoint. Then we have time to event endpoint, and recently published with delayed events. We published that in this year. And we published a paper about multi-arm continuous endpoint in 2018. So what is work in progress? Well, work in progress is what I'm already finished 95% of, is a two-arm unbalanced allocation continuous primary endpoint scenario. That was a really tricky thing, and I come to this in a couple of minutes. I hope to publish that next year. Then I have a master student, Alina Müllmeister, who did group sequential designs for continuous endpoints. And I have a master student, Steffi Schönen, who do the multiple endpoint scenario within our innovation project, RIMA. She did that for us. And what we would like to do is for slope models with linear mixed effects models, and for the binary case, well, that is done by Martin Reugels from my department. He's working on that. So you might think, okay, and what is coming out? Well, that's not a general recommendation. It's just a direction in which it goes. So the two-arm continuous primary endpoints makes it clear that that we have elevated type 1 error probabilities with larger studies. That I showed just a couple of minutes before. For the multi-center situation, which you can compare similar as a stratified analysis, we saw that similar with stratified and unstratified randomization, so the effects are similar. Similar with unbalanced center sample sizes, and elevated with larger number of centers. So larger number of stratification factors are worse, because it's, of course, it's more predictable. Two-arm unbalanced survival primary endpoints affected by test statistic, type, and strength of the allocation bias and the randomization procedure. I think we do not have a very, very clear direction in that. It depends on the situation you have. And the multi-arm continuous primary endpoints, so the type 1 error probability is elevated by more groups. So now I'm coming to my special cases, the orange ones, the two-arm sequential continuous endpoints elevated to a larger number of stages. More stages brings more type 1 error probability, and fairly similar with Pocock's and O'Brien Fleming's design. These are the two designs we evaluated right now. There are a huge number of other procedures. And now I'm coming to my pretty small baby with the unbalanced allocation. Well, I'm studying that right now. And what I found is that if you know the allocation ratio in advance, what is often described in the informed consent for the patients, then the type 1 error probability is affected much more than in a 1-to-1 allocation ratio, because you can better predict. But on the other hand, if you do not, if you do not say or tell the people what the allocation ratio is, then the type 1 error probability goes dramatically wrong. So my recommendation is don't tell anybody about the allocation ratio in advance. I will write that paper, hope it will be accepted. So what is about real application? Well, I cannot tell you so much about that. Only with that point which was mentioned by Rima. I did some work with Jörg Schulz and Katrin Reetz together about Friedreich ataxia, and we developed this model for the progression characteristic of Friedreich ataxia patients from the EFACTS register for 2-year cohort and 4-year cohort. And from this, we saw, okay, we should, they would like to do a randomized clinical trials, the NICOFA trials, where they would try to validate nicotinamide in patients with Friedreich ataxia against placebo. And we planned this trial. Okay, and here the story begins, and we have a paper with the protocol, and you can read there that we would like to implement the best practice randomization procedure to minimize the impact of selection and time trend bias on the type 1 error by using the ERDO. And we did that. No. You cannot expect that I will tell you now what is coming out of this process because the trial is running and that is confidential. I will not give you the information, which is the procedure we selected. We have to wait until the trial is finished because the ERDO statement and the report is confidential until the database is closed, right? To preserve consumers. So I'm summing up. Too fast, I guess. So the ERDO provides you a good way of structured scientific selection of a randomization procedure, which avoids mostly the bias in a trial and can be used because there is an underlying bias model for this, which can be used in a sensitivity analysis at the end of the trial to understand whether biases affects your trial. So that's a good story because we have a bias model. Okay, and that should be a report which is confidential to the group which is involved in the trial and can be opened at the end and can be done. So what are we doing in the future? The journey continues. We do this evaluation, this sensitivity analysis for the EPISTOP ideal data. So the EPISTOP trial was in epilepsy patient, and the coordinator of this EPISTOP ideal project is Rima Nabout, and I'm very, very, very exciting and happy that I can work with her in the future about this. And we do this simulation, and we'll find out whether allocation bias is present in the data. And what this also can help is if we know for this form of trial which kind of allocation bias may be in the trial, we can use this for future planning. So if we see, for example, there is only 10% allocation bias, we can use the 10% for planning our next trial as well. So we can increase our knowledge as it is. And also in the iStore and in the evidence R&D innovation projects where I am involved in and also Alex is involved in, we will consider randomization process. In the iStore project, we will do this stuff with the multiple endpoints. What is a good model so that we can provide a similar analysis for this? And in the evidence R&D, I will use and develop together with Alex and together with Nicole randomization-based inference procedures, which help us to evaluate trials in a limited or finite population. What is about inference if only 8 patients are involved in the world, and I can include them in the trial? So how to do that? Randomization-based inference, I am sure, will be solution, but let's try to figure out. Alex, I count on you, and Nicole as well. Okay, to sum up, I'm too fast, I guess. Maybe you have questions. So randomization is important in assessing clinical trial validity, but we have a model. And by this, we can quantify the effect of bias, and that brings another perspective into the discussion. Randomization and selection of the best performing procedure is now available because we have the software. The software is a so-called, it's called Randomizer. It's an R package which you can download for free, and there is also this vignette and description and so on. Yeah, and well, that's helpful in that direction. So can be done. The ERDO provides a useful approach, structured approach, so you know which steps you have to do, combined with the randomizer software. Oh, it's written here also here. An efficient tool for improving RD clinical trials, and estimate of bias can now be used in evidence synthesis or health technology assessment included in these processes, because we have now data for the effect of the bias, and we will evaluate that in EPISTOP IDEA. Within the EJP RD innovation project, ISTOR and evidence R&D, we will use the third part of the benefit of randomization, the randomization-based inference, and I hope the community can profit from our research to do clinical trials in limited or finite populations. And with that, I thank you all for participating or listening to my talk, and I will finish here.